Hello everyone, in today's class we'll go through the final concentration in a gas phase. Previously we were using this equation here, Ca equals Ca naught times 1 minus x. At the course we were using this equation in the course. This equation only applies for incompressible liquids, only used in the liquid phase, which relates the initial concentration with the conversion rate in order to find the final concentration. Well, in the gas phase, to find the final concentrations, there's a couple factors you need to take into consideration. One is the expansion factor, which is based on the density of the gas. Gases tend to change their density as pressure is being applied. There's also other factors that affect the concentration in the gas phase, which is pressure and temperature. But the main reason is that gases throughout the reactor do not have a constant density due to pressure, whereas in incompressible liquids, the pressure is constant throughout the reactor. Therefore, the pressure stays the same, resulting in density staying the same. Therefore, we can use this equation right here. So back to this equation, which is used to find the concentration, the final concentration in a gas phase. In this class, I'll show you how that formula is derived. Okay, let's go ahead and start. I'll erase this. Okay. Let's go ahead and drive this equation right here. So to begin, we first start with the total concentration, the total final concentration over the total initial concentration, which will equal, as we've done previously, we know that Ca equals the molar flow rate over the volumetric flow rate, which is Q in this course, just to avoid any confusion. Okay, so Ct will equal Ft over Q, and Ct naught will equal Ft naught over Q naught. Now, when dealing with gases, we'll use the ideal gas formula, which is PV equals nRT from thermo. In this course, the volume, we'll use it as the volumetric flow rate, and the moles will be the molar flow rate in terms of A. Okay, RT will stay the same. Now, if I want to rearrange the equation in terms of FA over Q, that will equal to P over RT. Okay. Now I can go ahead and substitute this here. Therefore, Ft over Q divided by Ft naught over Q naught will equal to, actually this is Ft. Okay, will equal to P over RT divided by P naught over RT naught. Okay, let's go ahead and clean up this a little bit. In the left side, Ft divided by Ft naught times Q naught over Q will equal to P over P naught times T naught times R over T times R. Okay, the R will cancel because it's constant. And we'll move this term to the other side because we're solving for Ca, which is which is in the Q. Okay, so when we move this term to the other side, the numerator and denominator will switch. Okay, therefore Q naught over Q equals P over P naught stays the same. T naught over T times Ft naught over Ft. Okay? Now again, we know that Ca equals the mole flow rate over the volumetric flow rate. Therefore, Q will equal Fa over Ca. You can substitute this here, and we'll be left with Q naught divided by Fa times C, which is basically simple math. I'll go through it. Q naught divided by Fa over Ca, which is the Q, can also be written as Q naught times Ca over Fa. When we change the sign, we can flip the denominator and numerator. Therefore, that will equal Q naught Ca over Fa. Okay? So we'll use this directly here. Actually, I can just copy and paste it. Okay? That will equal P over P naught. The right side hasn't changed. T naught over T times Ft naught divided by Ft. Okay? Now we're going to isolate for C, so we're going to take these two terms to the right side. Therefore, C equals Fa divided by Qa times P over P naught, T naught initial temperature divided by final temperature times Ft naught over Ft. Okay? Now we know that Fa equals Fa naught times 1 minus x, and Q naught equals Fa naught times Ca naught. Okay? So same thing, we'll substitute these two into the equation. Ca equals Fa equals Fa naught 1 minus x divided by Q naught, which is Fa naught times Ca naught. Okay, and everything else is the same. P over P naught, T naught over T, and Ft naught over Ft. Okay, these two will cancel, and we're only left with this term here that needs to be adjusted. So to understand that term, we need to understand Ft. Ft equals Ft naught plus Fa naught gamma. Give me a second. Gamma x. Yes. Okay. And if we divide this by FTO, we will get 1 plus Ya naught, this Fa naught divided by the initial final concentration, final flow rate, sorry, will give us Fa naught, okay, times gamma times x. Okay, that's Ft over Ft naught. Okay. Now this term here is called the expansion factor, which is symbolized by sigma or epsilon, sorry, symbolized by epsilon. So Ft equals Ft over Ft naught equals 1 plus epsilon, which is the expansion factor used in gas phase, 1 plus epsilon times x. Okay, but as you see in our equation, we're given ft naught over ft. So if we flip it, ft naught over ft, that will equal 1 divided by 1 plus epsilon x, and that is the last term that we need to substitute into the equation. Okay, but before we do that, let's understand this step here. I kind of rushed through it. So as I said, fa naught divided by ft naught, which is basically the initial mole flow rate of A divided by the initial total moles, okay, which gives you the mole fraction, the initial mole fraction of A in the gas phase, and that's why we're using Y. Okay, so that's simple. But what is gamma? Gamma is basically the change in moles. Okay, that's this expression right here. So it's a change in moles, meaning, let's say we have a chemical reaction, A plus B gives us C. Okay, so there's 1 moles in the products being produced and 2 moles in the reactant. So gamma will equal the moles being produced, 1, minus the amount of moles being reacted, which is 2. That will give us -1. Gamma here is -1. But if we look at another chemical reaction, A gives us B. Okay, so gamma here will equal 1 moles of product being produced minus 1 moles of reactant being used. Gamma here is 0. So in a example where the chemical reaction is equimolar, the gamma will equal 0. If gamma equals 0, the expansion factor will equal 0. So expansion factor is the initial mole fraction of A times gamma. Okay, so if that's 0 due to an equimolar reaction rate, a chemical reaction, the expansion factor will be 0. That will cause this term to also be 0, therefore this whole term will be 1. Does that make sense? So let's go ahead and substitute that. So yeah, this is how you get your gamma, which is from the chemical reaction. It's the change in moles. Your epsilon, your expansion factor, depends on gamma. When gamma is 0 due to an equimolar chemical reaction, your expansion factor is also 0, leaving this term to be 1. So if I bring this down here, this equation, which is, after simplifying it, Ca equals Ca naught 1 minus x divided by this here, 1 plus expansion factor times x, and that is P, what's left is P over P naught, T naught over T. Let me double check. Yes, T naught over T, P over P naught. Yeah. So we substitute 1 over 1 plus epsilon x in this term here, and this is the final equation for the concentration of A in a gas phase. Okay, so as we said, if the chemical reaction is equimolar, this term here will be 1. Okay, if you're working with isobaric, if you're working with an isobaric problem, meaning that the change in pressure is 0, therefore the final pressure equals the initial pressure, this term P over P naught will equal to 1. So that will equal to 1. Okay? If you're working with an isothermal problem, meaning that the change in temperature is 0, meaning that the final temperature equals to the initial temperature. Therefore, this term here, T naught over T, will equal to 1. So this term will also equal to 1. So if you find yourself working with an equimolar, epsilon equals 0, and isothermal, and isobaric in a gas phase, you'll use the first equation that we've been using in incompressible liquids. You'll use this formula here. Okay? But in most gas phases, that's not the case. The reaction is not equimolar, therefore epsilon does not equal 0. Okay? There is a change in temperature, and there is a change in pressure. Therefore, for a gas phase, you'll find the final concentration using this equation. 1 plus epsilon times x times P over P naught times T naught over T. That's it for this class. See you on the next one.